This week we're going big on the environment, but can we fight or even understand the changes we're inflicting on the planet?
Well, we're in Iceland pulling CO2 out of thin air.
Talking of thin air, we're high up in the Alps monitoring melting snow.
And how do you find out what lives in a rainforest? Well, here's one high-flying idea.
I'm being swabbed.
Snow, icebergs, glaciers, continental ice sheets. If it's white and cold, it's part of the Earth's cryosphere. And it shouldn't come as a surprise to learn that that is getting smaller. Working out what's melting and where is important. And up here, nearly 3,500 metres above sea level, we've come to the High Altitude Research Station overlooking the Aletsch Glacier in the Alps. Switzerland is home to 1,400 glaciers, of which Aletsch is the biggest. And it's here that we find groups of scientists developing new techniques to watch the ice and snow and monitor their retreat.
Glaciers are water reservoirs that we have, which is important for groundwater repletion. I think this is an important fact. But also, if you lose this mass, you have instability in the mountains, so you have more landslides ongoing, more erosion.
It is also a cause of natural hazards, avalanches if there's a lot of snow, and rock falls and similar things if there's not enough snow and the ground destabilizes. A very important one in terms of the energy transition is the hydropower generation. Hydropower generation uses the water that runs down from the mountains, and if there is not enough water, they cannot generate enough power. And if there is a lot of water, a lot of snow, they actually need to know this in advance to plan the generation. For all this, we of course need to know where the snow is, because that is the water of the future.
There are two new methods being developed here to not just monitor the surface, how much it's melting, how fast the glacier is moving and so on, but also to find new ways of seeing below the surface.
These two top antennas are transmitting antennas, and here we have a set of receiving antennas.
So the two different radars, this gives us a different, let's say, angle and perspective. And with this, we can get an extra information that otherwise we will not be able to acquire.
Esther and Marcel's team is using radar to penetrate deep into the snowpack. Now, different formations of ice crystals reflect the signals back in different ways, revealing the internal structure of the snow, how deep it is, and how dense it is. After several weeks of taking measurements on snow cover across the glacier, the team will spend the next few months evaluating that data to discover whether radar really can shape future studies. But from the ground, you can only see so far. To get a wider view, you need the second method and go even higher up than this.
The space measurements are needed to cover the area. It is simply impossible to cover a large area like the entire Alps with ground-based measurements.
Conrad's project is training an AI system to predict what will happen to the snow next. The system has been trained on images from ESA's Sentinel-2 satellite network. These are a mix of optical photographs that we'd see with the naked eye, images in the infrared, and some created using longer wavelength radio waves like Marcel and Esther's ground-based system.
So what our model effectively does is it creates a time series. The satellites pass over every couple of days, and it's like a very slow motion video of the surface. And we acquire this video and process it. In our case, we have a local snow depth pattern, and we want to predict, with the help of the sequence and also the new observation, what will be the next snow depth pattern.
Now, these techniques are still in the experimental stage. If the teams can improve their methods, then they will no doubt prove invaluable in monitoring how the warming climate is changing snow cover around the world.
For example, in Greenland, we have a huge area where we are looking for supraglacial lakes, we call them, which are lakes beneath the snow. The amount of lakes are giving an indicator also of global warming, and we can detect these lakes actually with radar signals. They are built up in summer where you have no snow on top, and in winter where you have the accumulation of snow, you can still see them beneath.
In fact, these techniques could be used even further afield.
We have radar systems which are observing the Venus, for example. And on Venus, we have a very strong atmospheric contribution. And in order to go through this atmosphere, we need longer wavelengths, so radar wavelengths to penetrate through it and then to see or to characterize really the surface of Venus.
Venus famously suffered a runaway greenhouse effect that's made it the hottest planet in the solar system. And while Earth's greenhouse effects won't be anywhere near as bad, we have to fight its effects. And Adrian Murray has been looking at a promising solution back on our world. Or at least, I think it is.
This isn't some faraway planet. These Martian-like landscapes are found in Iceland. It could almost be a scene from science fiction. Seemingly in the middle of nowhere, these towering machines are guzzling up carbon dioxide, a global warming gas. So, could this much-hyped technology help us fight the climate crisis?
Mammoth is the world's largest direct air capture and storage facility. What you see here are 12 of our collector containers. When the plant is fully operational, we'll actually have 72 around the plant. That will enable us to capture 36,000 tons of CO2 every year.
It works like a giant vacuum. Each of these units is the size of a shipping container and has a dozen powerful fans sucking in the surrounding air.
They pull in an Olympic swimming pool's worth of air every 40 seconds. And then inside, a filter separates the CO2. In the atmosphere, its concentration is very dilute. Capturing even small amounts requires lots of energy. And Mammoth gets both power and hot water from the nearby geothermal plant.
For us to do direct air capture effectively and efficiently, we want to make sure that we're using energy that has a low carbon footprint.
Some would look at this and say, hang on, where's the industry? Would it not be more efficient to have one of these next to a factory that's actually making the pollution?
Carbon dioxide tends to just disperse and diffuse in the air. The effectiveness of direct air capture is not dependent on being located close to industrial emitters.
Okay, I'll let you show me where the CO2 goes.
That lowest line here, that's actually the CO2 that's coming from those 12 containers outside. These two balloons are a really good visual representation of what, in total, 1 ton of CO2 looks like.
This tower then works a bit like a soda stream, dissolving the pure CO2 in water.
From the top we have water coming in, so it's like a shower. It's sort of at home if you're making sparkling water, same idea.
That fizzy water is sent to these igloo-like domes.
So here we have one of our injection wells. Please come inside. This well is going 700 meters down into the underground here.
The CO2 and water is pumped deep into the basalt bedrock, where it reacts and turns to stone.
So you've got a couple of rocks
Yes,
there.
exactly. I'm a geologist, so I brought rocks. This is a fresh basalt here, actually from one of the last volcanic eruptions here in Iceland. You can see there's a lot of porosity in here. Here you can see there's a lot of these pores now filled with white specks. Some of these contain the mineralized CO2.
And Kopfik says that happens pretty quickly.
We're not talking about millions or tens of thousands of years. Around about 95% of the CO2 was mineralized here within 2 years in the pilot project. This is incredibly fast, geologically speaking.
Mammoth is Climeworks' second commercial plant and almost 10 times bigger than the last one, collecting 36,000 tonnes of CO2 annually, about the same amount as taking 8,000 petrol cars off the road. But it costs a whopping $1,000 to remove just 1 tonne.
What do we mean by removing emissions?
Among its customers are Microsoft, H&M and Lego. Worldwide, more plants like these are on the way, though they'll still only remove a fraction of what's needed. And despite calls to slash our emissions, the CO2 we churn out continues to grow.
Do you think direct air capture can be an effective tool for removing carbon?
We release about 40 billion tons of carbon dioxide to the atmosphere every year, so this won't make a dent into the big problem. But I think you should use all methods and methodologies to fight this problem.
What's it going to take to scale it up, bring costs down and make it really impactful?
By the end of the decade, we want to be at a cost of capture of between $300 and $400. Technology improvements will help drive down costs. A second lever will be scale.
The team says this is just the beginning. Mammoth will soon be dwarfed by another much bigger plant, Project Cypress in the United States, which will eventually capture 1 million tonnes of CO2 each year.
From Mammoth to Cypress, we're now looking to break that hundreds of thousands of tonnes of capture capacity a year. I really do believe direct air capture and other engineered solutions are going to be able to get us to the point that we need to help fight climate change.